There are trillions of planets in the universe, but even with our most powerful telescopes, we've never found a single trace of life out there. And no alien civilizations ever found us. It could be we're just not advanced enough to be noticed, or looking for the wrong things. So it's time to upgrade, make some interstellar noise, build some megastructures, megascopes, and find out whether we're actually alone in the universe. Today, we're going to speed up Earth's evolution and become an intergalactic Type 3 civilization on the Kardashev scale. That is, if we don't go extinct first. Of course, to become a Type 3 civilization, well, we'll need to reach Type 1 status first. Because currently we are... that's right, 0.73. The scientists ran advanced machine learning computations a couple years ago, and the math said that's where we are on the Kardashev scale, which doesn't sound very impressive. Now, if you're wondering, what the heck is a Kardashev, and what's their scale, and what does it have to do with civilization? Well, that's completely fair, so let's back it up. The Kardashev at the heart of the Kardashev scale is Nikolai Kardashev. He was an astrophysicist and scientist, part of a team looking for extraterrestrial signals in the 1960s. In 1964, he wrote a short, elegant paper, Transmission of Information by Extraterrestrial Civilizations. It proposed that signs of life strong enough to cut through the universe's noise required civilizations that controlled and used staggering amounts of power to generate that much information, typically going out into the universe as radio signals. So Kardashev classified them into 3 straightforward levels of civilization, starting with... Kardashev described the Type 1 civilization as a civilization that controlled and used all the energy resources of its entire planet. In our case, that would be harnessing and using all the energy on Earth. So solar, wind, geothermal, fossil fuels, tidal energy, nuclear energy, fidget spinners, all of it. A Type 1 civilization would have full control over its domain. Control over weather, over the power of tectonic plates, volcanoes, earthquakes. Clearly, this requires technology that's far beyond where we are currently. So, we're moving slowly toward Type 1. Very slowly. Recent studies predict that we'll barely reach 3/4 of Type 1 by the year 2060, and it could take another 300 years after that, or more, to actually reach a full Type 1 civilization status. Which means, yeah, you're gonna have to put up with bad weather for a while. Now, if you're thinking, hey, I'd like to be around when we get better weather, how can we speed this thing up? Well, good question. Harnessing and utilizing that much energy is gonna require capturing all the solar power striking Earth and figuring out nuclear fusion, or digging up and burning every bit of fossil fuel that exists, which would have its own catastrophic effect on the weather. Okay, as everyone reaches for the phones to ask their favorite bot how we speed this up, yeah, the one glaring answer is artificial intelligence. And it's already in motion. Scientists at the UK Atomic Energy Authority are already bringing AI supercomputers online to help accelerate nuclear fusion research. DeepMind Learning recently revealed the structure of millions of new inorganic crystals that could be used for all kinds of technology, creating work that researchers estimated was the equivalent of 800 years of knowledge. So, great, maybe AI can help us get there fast. If it does, and we're able to harness all that energy, what would it be like on a Type 1 civilization? Well, we'd have cracked fusion, so we'd have what comparatively feels like infinite energy. We'd have control over our environment and the weather, so it would be temperate. It'd likely be more of a global community rather than a nation-state-centric planet, as we wouldn't be competing for oil in the same way. And ideally, we'd all have a basic universal quality of life, as we'd all have the energy to feed everyone, provide clean water and tech for everyone, and turn deserts into greenhouses. We'd have excellent travel, technology, medicine, materials, and we'd be starting to set up outposts in the solar system. Our AI-assisted civilization would be making some noise. Sounds idyllic and kind of straightforward, right? The Industrial Revolution took a few hundred years to get us to this point, so if it's only going to take a few hundred more AI-assisted years to become a stellar superpower, it raises another question. Why haven't we found any evidence of any other Type 1 civilizations in the entire universe? Or, in the words of the great physicist Enrico Fermi, who over lunch with his fellow scientists muttered the famous line, "Where is everybody?" In short, the Fermi paradox is the idea that if there are trillions of galaxies, each with billions of stars, there could potentially be billions of civilizations out there. So why haven't we spotted one? And even if our instruments aren't precise enough to spot them, then why haven't we heard from a Kardashev Type 1 civilization? Or a Type 2? Or a Type 3? That's the idea Enrico Fermi threw out to his colleagues over club sandwiches in 1950, and we've been chewing on it ever since. The Drake equation, formulated in 1961, tried to quantify Fermi's paradox by estimating the vast number of stars and planets and comparing them against the fraction of planets where life could have evolved, as well as calculating how long those civilizations survived after reaching high-tech capacity. And the math says we should see another civilization, or millions of them, because there are so many planets out there. Just in our galaxy, estimates range from 1 or 200 billion to 1 trillion planets or more. That said, we've only discovered about 6,000 exoplanets to date. That's it. So there's still lots of room to search, but you'd think we'd have seen one sign by now. One megastructure, one anything. So if there's no sign of any other civilization, maybe there's a reason for it. And that reason is, maybe the reason we haven't spotted any other civilizations out in the cosmos is that they just don't exist. Maybe there's exactly one civilization that's achieved the ability to broadcast. Us, doing what you and I are involved in right now. Maybe that's it. But if that's the case, with the trillions of planets out there, there must be some sort of great filter that stops civilizations from reaching Type 1 sophistication. That's the idea that Robin Hanson floated in the late 1990s, where he laid out a number of hard steps that could potentially prevent intelligent civilizations from arising. It could be that some of these steps are nearly impossible. From the chemistry necessary to create life, to the Goldilocks nature of the planet needed to incubate it, to the leap from single-celled organisms to viable multi-celled life, and, figuring out how to do electronics. These steps took about 4 billion years on our planet, so we know it wasn't a quick, easy process. It could be that we're actually past the Great Filter, that we're one of the first civilizations to go from basic amino acids to functioning, broadcasting, energy-harnessing communities. Or it could be the Great Filter is still ahead of us, that civilizations reach a point where they can broadcast, even create interstellar probes with golden records, but they eventually, inevitably, destroy themselves. I mean, we came awfully close during the Cold War, where one rogue officer or faulty communication could have started the Third World War. We could have unloaded 70,000 nukes on our own planet. That would have kept us from reaching Kardashev Type 1, because, mutually assured destruction. And hey, we still have like 12,000 nuclear weapons kicking around, so we still really have to be careful about it. Fossil-fueled climate change is another long-term threat to our survival. The other option for the Great Filter? Artificial intelligence. We're all thinking about it. With the rise of LLMs and autonomous AI agents, looming artificial general intelligence, there are tremendous possibilities for accelerating humanity toward a Type 1, 2, or 3 civilization. But there's also the possibility that civilizations across the universe create what's called misaligned artificial intelligence, and it wipes out the civilizations that created it. We all tend to invoke Terminators or Judgment Day, and hey, there are autonomous AI drones in combat these days, so it is a working possibility. It's also possible that a rogue bot that doesn't understand the consequences of its actions creates a biological pathogen that kills every creature on the planet. An AI-created super pandemic. Or a bad actor uses AI without safeguards to create a chemical that devastates our ecosystem, or shuts down our power grids, or we become so dependent on AI that we can't do anything without it. We can't raise our kids or raise our crops, and when adversity hits, we've lost our ability to do even the most basic human tasks. The great silence out there might be evidence that most civilizations don't navigate this transition to the supercomputer artificial intelligence era and survive. Is it possible that artificial intelligences always destroy their founding civilizations? Is a universal law, like thermodynamics? Well, it's possible. So maybe we should be thinking, what do we want to do differently? What if we're at a bottleneck where our choices really matter? The way we work with AI, the constraints, the oversight, the laws around AI usage and development, they could all be critical to whether a civilization, let's face it, our civilization, makes it to 0.75 on the Kardashev scale, let alone Type 1. What if a civilization's foresight regarding AI capabilities is what determines whether or not it makes it to the next Kardashev level? Remember that open letter a couple years back that all the computer scientists and godfathers of AI signed, asking for a 6-month pause on AI training? With people as diverse as Jeffrey Hinton, Elon Musk saying it was time for sober second thought? Maybe it's that kind of community-minded thinking, of societal resilience, which makes better choices in regulating the types of AI that are built. Maybe that's what allows a civilization to survive. Or, as some scientists have noted, it would be safer to focus on building narrower, tool-like AIs, instead of building wide-functioning, agentic AI that can do almost anything. Maybe specific types of AI with built-in guardrails and guidelines can help us become incredibly productive and reach Type 1 without wiping ourselves out. That's possible. If so, and if we can avoid an AI-driven Great Filter, then maybe it helps us reach. Now, if our civilization is careful and thoughtful enough to overcome the Great Filter of AI, humanity would eventually progress to a Type 2 civilization. To reach Type 2, the decisions we make this decade will have a butterfly effect that will impact untold future generations of humanity. Because AI isn't slowing down, it's accelerating. In just the last 6 months, we've seen a 50% increase in AI usage per day. Personally, I want to see what comes out of a Type 2 civilization. Kardashev described it as a civilization capable of harnessing the energy radiated by its own star. So we'd have the full power of the sun at our disposal. How much energy is that? Well, Take every power plant, every solar panel, every ounce of energy we produce on Earth in a day, and you wouldn't even be close to matching the sun. Now, collect that energy for an entire year, and then do that again for another 639,000 more years? Well, then, and only then, would you match the total energy that the sun kicks out every single second. Yeah, Type 2 civilizations are pretty hungry. It would require a lot of building to get to that point. We're talking about creating mega constructs around the sun, designed to capture its phenomenal power. Just the amount of raw material it would take. We might be talking about strip mining Mercury or Mars down to the core to build Dyson spheres or Dyson swarms. If you're a science junkie like most of us, well, you've probably heard of a Dyson sphere. It's not a new kind of vacuum. It's basically a theoretical metal ball that civilizations would build around their star to capture all the starlight. Freeman Dyson cooked up the idea in 1960, saying, within a few thousand years of industrial development, any intelligent species should be found occupying an artificial biosphere which completely surrounds its parent star. The idea has led to all kinds of sci-fi novels, movies, along with deep research on the actual engineering. Maybe a Dyson sphere isn't possible to start, but maybe a Dyson swarm could be. Imagine millions or billions of satellites in orbit around the sun, capturing and focusing its power. Or we might be able to build a stellar engine, a massive sphere or disk that captures the energy of the sun and uses it to move the entire solar system. Or gargantuan, phenomenally powered laser arrays that could be used to move asteroids or trans-Neptunian objects around the solar system for raw materials. Need some water? Well, zap that incoming comet. It all sounds crazy, but these things were pure science fiction 60 years ago when they were props in the original Star Trek. I'm just saying, speculative science matters because here we are, able to communicate worldwide with the flick of a button. Does that make William Shatner the father of modern telecommunications? Now, these Dyson swarms and stellar engines aren't going to happen overnight. Even with cooperative AI, it's going to take at least a couple of thousand years. And by that point, humans and our AI agents could be melding. Yeah, well, if we're going to survive in space, we'll have to be genetically modified, and quite possibly directly interfacing with technology as we strive to reach a Type 3 civilization is a theoretical civilization that's in possession of energy on the scale of its own galaxy. So, for us to reach Type 3, we'd have to harness the power of all 100 billion stars in the entire Milky Way, and the black hole at the center of it, Sagittarius A star, using theoretical constructs like a magnetic harness or some system yet to be discovered to capture the energy found in the black hole's accretion disk. Massive Dyson swarms and stellar engines would have the ability to push stars closer together to better capture and utilize their energy. They'd be controlled by other theoretical structures. Supercomputers like Matryoshka brains, giant computers the size of a solar system, powered by trillions of humans who've uploaded their minds to the computers. That's mega structures. Omega structures. I just made that up. But if you want to lump me in with Kardashev and Dyson, that's fine. We could build megascopes to look for other civilizations across the universe, which would help put Fermi's worries to rest and find out whether humanity really is the first species to get past the Great Filter. Now, even with the help of benevolent AI, this stage would take hundreds of thousands or millions of years, and we'd still be constrained by the speed of light. Even if we built tech that can achieve near light speed, The Milky Way is a minimum of 100,000 light years across, so it'd take a long time just to stretch our presence throughout the stars. It's possible we could use von Neumann probes to spread across the galaxy. Von Neumann probes are small probes designed and built to travel afar, settle down on a distant moon or planet, and set up a self-replicating system. They'd use the raw materials of the new planet to build more probes and send them shooting off toward the next system. Once a civilization has reached Type 2 or Type 3, covering an entire galaxy with its footprint, it doesn't take that long in the cosmic scale of things, which is why it's weird that we haven't seen anyone else do it. Soon, humans would have their representatives hurtling across the entire galaxy and heading into the next, Andromeda. It's only a couple 100 million light years away. Now, you notice I said representatives. Look, if Earth becomes a Type 3 civilization, maybe the first Type 3 civilization, it's hard to conceive how it does this with humans and machines as we know them today. We'd likely be a mix of human and machine, some sort of deeply interconnected galactic internet super beings out there creating that massive radio signal. And whatever we could think of, we'd probably be able to do it through a hybrid of artificial and natural intelligence. But getting there means learning to work with artificial intelligence to avoid any possible great filter threats that it might present. And maybe together we can solve the greatest future threats that humans and artificial humans could face. Like our sun becoming a red giant in 5 billion years.
Imagine a future world where you have endless supernatural powers. You can hop through the multiverse and bend time to your will. You'd be part of a super advanced version of humanity, a Type 7 civilization. Yes, please. But how do we get here? Today, we're taking you on a journey to the future to show you how humanity could progress from a Type 0 civilization all the way to a Type 7. Now, before we visit these super advanced civilizations, let's take a second to talk about the scale we measure them on, the Kardashev scale. For starters, you're probably wondering why it's called the Kardashev scale. Well, this scale is the brainchild of Russian astronomer Nikolai Kardashev, who proposed a system for classifying how advanced a civilization is. It's kind of a tricky problem because civilizations change over time. Take weapons, for instance. In the Stone Age, having a really sharp stone made all the difference. But it's hard to measure advancement based on how many sharp stones a society had, because now our weapons are all bombs. Kardashev realized he needed to hit on a metric that's a fundamental characteristic of civilizations. He decided that had to be energy. He classified civilizations by how much energy they're able to harness and use. Now, Kardashev only defined Type 1, 2, and 3, but others have since expanded on his definition to add Types 4 through 7. Okay, now that you know what the scale represents, let's take you on an epic tour to explore each of these civilizations. Our first stop, naturally, a Type 1. But before we set off for a Type 1, let's take the pulse on where we are today on our blue marble. Well, Type 0. Yeah, despite all the progress we've made as a species, we're living in a civilization that still hasn't reached the first rung of the ladder. Heck, we're still burning dead plants for energy, using just 1/1,000,000th of the energy that the sun splashes on our planet. And we have zero control over natural disasters. If a supervolcano erupted tomorrow, we'd all be dead. Now, you're probably wondering, are we really a zero? Has all the progress we've made over the last hundreds of thousands of years meant nothing at all? Well, things aren't that bad. Scientists have crunched the numbers, and what they found is that we're actually at a 0.72. So close. We're at a Type 3/4. They estimate that in 100 to 200 years, we'll get to a level 1, but instead of waiting that long, let's take a trip forward in time and see what that feels like. Type 1 civilization. Welcome, you've arrived on a Type 1 Earth. You know, if Earth is ever going to reach the technological heights of a Type 1 civilization, well, energy and clean power will be key pieces to making this dream a reality. Energy is crucial because it underpins technological advancement, economic growth, and environmental sustainability. All the things we need in order for us to become an advanced society. Now, in order to make progress towards these aspirations for the future, we need to focus on finding solutions today, like creating cleaner and more efficient electrical systems. Humanity will also need things like quantum computing and artificial intelligence to produce unprecedented technological advances. The medical breakthroughs we uncover have us living in a world free of cancer. You could have bionic limbs, and your overall lifespan is much longer. Interplanetary travel is also a regular part of life in a Type 1. You might want a vacation on the Moon or Mars. And those crazy floods, Category 6 hurricanes, and tsunamis of the 21st century, they're a thing of the past. With this new supercharged energy, we'll have the power to reduce a Category 6 hurricane to a Category 2, or make it go away completely. That asteroid that's hurtling toward Earth? Well, no worries, you just press a button and nuke it. Congratulations, you're no longer in danger of being wiped out by natural disasters. It's safe to say that living in a Type 1 civilization would be life-changing. And that's not all. The way we communicate would be incredibly different. English has now become the unifying means of communication around the world. The internet has connected everybody on Earth, and we now have a single global currency for international commerce. And you're part of a more tolerant society, guided by science and reason, more unified as a single planet. Life on Earth is great, but the colonies on Mars and the Moon have whet your appetite. You're itching to explore the rest of the solar system. Well, what's stopping you? You just need a little more energy. Type 2 civilization. A Type 2 civilization is defined as one that's able to harness all the energy from its star. For you, that's the sun. How long will it take humanity to reach this point? Well, if you're around long enough to see this happen, it'll be a few thousand years. You're now harvesting all the possible energy from the sun. To do this, you've built a Dyson sphere around the sun, or maybe you've built a Dyson swarm, a megasystem of smaller structures that orbit the sun, gathering its energy. Now, whether it's a sphere or a swarm, this megastructure collecting sunlight and radiating out this energy creates a distinctive signature in space, the signature of a Type 2 civilization. Now, this could be detected by other advanced civilizations looking for signs of life. Who knows? You might finally get a call from those elusive aliens. You're now part of a true multi-planetary society. Using the enormous amount of energy harvested from the sun, you make other planets and moons in our solar system habitable. Over a period of thousands of years, there are now fully functioning Type 2 colonies on Mars and our moon. Also on Venus, Europa, and Titan. Using advanced genetic engineering, we've modified our bodies to quickly adapt to different conditions on different planets, and to modify extreme conditions on other planets using weather engineering techniques. That poisonous gas on Venus, well, you get rid of it, and you'll mine other planets and asteroids in our solar system for their natural resources. I hear Jupiter is a great source of hydrogen. Now that you're free from the danger of being wiped out by catastrophic natural disasters on Earth, you're feeling invincible. Is there anything to worry about? Well, unfortunately, yes, you can still be wiped out by a cosmic scale disaster. For instance, a supernova explosion. It's the last stage of a dying star. If a supernova's blast wave strikes a dense cloud of gas around it, enormous amounts of X-rays could be produced, and these could damage the atmospheres of planets up to 160 light years away. An event like this could wipe out colonies on Earth and nearby planets. But come on, after so much progress, humanity isn't going to let some pesky space bombs wipe us out. To make sure that life sticks around, we're going to have to level up and inhabit more than one star system. So now you've got a new quest. You need to harness more energy, enough to avert disasters on a cosmic scale. It's time to become a Type 3 civilization. If you can level up to a 3, you'll ensure that human beings become immortal. But you've run up against a problem. Stars in our galaxy are as far as 100,000 light years away, and you can't travel faster than the speed of light. Type 3 civilization. Okay, it's another 100,000 to 1 million years later. Welcome to humanity as a Type 3 civilization. You're now harnessing the energy of all the stars in our galaxy. But wait a minute, how did you get to stars so far away? And how did you choose which stars to go to? Well, first, humanity figured out how to achieve velocities close to light speed. Sci-fi tech like ramjet fusion and photonic engines are all in your toolbox. Next, you manufactured trillions of von Neumann probes. These are robots that can land on distant star systems, duplicate themselves, and repeat the process. Like ripples spreading out from the center of the pond, they expand out in our galaxy, landing on and analyzing all the stars. They'll figure out which ones are ripe for harvesting energy. Now, once the viable stars are identified, you send out a seamless Dyson swarm to surround them. Humanity is now the master of the Milky Way galaxy. You'll live on any number of countless planets engineered to your liking. You'll command the energy of billions of stars to do your bidding. Also, between the transition from Type 2 to Type 3, your body will have evolved even further. You'll be a cyberborg, a super intelligent being with the capabilities of AI fused with your biology. Genetic engineering techniques will replace clunky implants and lab-grown organs. You'll be able to regenerate worn-out limbs and other body parts. And as your bones wear out, your genome will be programmed to repair the skeletal wear and tear. You're not a vampire, but you'll effectively live forever. With life thriving in multiple far-flung galaxies, neither cosmic nor natural disasters can wipe out human civilization. You can avoid being hit by a supernova explosion by altering its path. Even if our solar system gets hit by one of these, human life will continue in other planetary systems in the galaxy. Congratulations! You're now part of an immortal civilization. But the Milky Way isn't enough for you. You're ready to explore the other galaxies in our universe. Type 4 civilization. Welcome to a Type 4 civilization. As part of a Type 4, you're able to harness the power and resources of all the galaxies in our universe. Now, we should also mention that going past the initial 3 types of civilizations is beyond the Kardashev scale that was developed, and a lot of the theories about these extra civilizations lean more towards science fiction than actual backed-up research. Nonetheless, they're still a lot of fun to speculate about, so let's get into these advanced and at times ridiculous civilizations. The technological capabilities of human beings at this stage are so advanced that it can be hard to even wrap your brain around them. In a Type 4 civilization, humanity has mapped out the entire universe, including all the galaxies and clusters inside it. You now have a deep understanding of every planet, galaxy, and star in the universe, the ones that are worth exploring and the others that are just massive rocks floating about. And with this level of knowledge, you'll come across other civilizations. Some of these are still in their embryonic stages, while others will be a little further along. Some might even be on a path toward annihilation, either because of their internal struggles or natural phenomena. Maybe, like any alien species that may be in existence today, you'll need to make decisions about whether or not to contact these earlier stage civilizations. You develop a set of intervention principles. Observing these civilizations becomes a fascinating exercise. You compare their progress with the history of Earth. But there's one pressing thing that keeps you up at night. Eventually, your universe, the only one you've ever known, will die. And with that, humanity will die out. To solve this, you aim your sights toward becoming a Type 5 civilization. You're ready to discover something even greater. Type 5 civilization. Welcome to the Type 5 civilization. Many doubted that humans could ever go beyond the edges of our known universe, but you've arrived at an even greater level of sophistication. You now control and harvest the energy from stars across multiple galaxies in multiple universes. How did you achieve this? A group of humans in the Level 4 civilization refused to let the human race die out with our original universe. Using technologies that I can't even explain here because they're so far beyond our 21st century comprehension, they helped humanity make the leap from single universes to the multiverse. But as humanity will soon find out, this is just the start. Type 6 civilization. Welcome to a Type 6 civilization. As a civilization, you can now pretty much control everything. You've uncovered the full set of universes that exist, and you understand their structure. In other words, you understand the omniverse. With these far-reaching abilities, you now see multiple timelines play out simultaneously. You think back to Earth's timeline, and you can't wrap your head around a time when humanity's level of knowledge was so minuscule. You thought ChatGPT and VR headsets were as far as humanity would go. Well, look at you now. For a while now, all your basic needs have been taken care of. Armies of robots grow and prepare food and construct shelters on planets of your choosing. Your bodies are cyber-human, living for as long as you choose. So now, the only question facing humanity is the age-old one. What will make us happy? Maybe it's power, maybe creativity, entertainment, or the further pursuit of technological advancement. A governing body oversees the omniverse. Human-AI hybrid leaders follow a broad set of guidelines to maximize the good for all. With your ability to take on any form, you experiment with your appearance. Maybe you have a wolfish grin, or maybe you're covered with fur like a kitty. Some human beings will experiment as living as bursts of energy. Either way, you can assume any appearance you like, but this is still not enough. Humans want to create more. A class of creative technologists bids for the opportunity to create new universes when old ones die out. Within these, they create and play with the new civilizations. These new universes push the boundary of space-time. Civilization starts to place some regulatory guardrails around this as the construction of new universes is in an early stage. Type 7 civilization. You've now reached an unimaginable level of progress. The guardrails of level 6 are off. You can create, alter, and destroy infinite sets of universes, giving you complete control of the omniverse. Multiple timelines across multiple universes exist simultaneously. You can see the past, present, and future all at once. Humanity splits into two broad groups: hedonists, who continue to value optimized human forms and seek lives of pleasure, and achievers who crave power and push the boundaries of technological creation. Did I say two groups? There's a third, which exists as pure energy. The new being you've transformed into exists in the form of higher consciousness. You've transcended all emotional states, and you're existing in a place beyond both happiness and suffering. You've reached a truly enlightened form. As pure energy, you're at one with every other human being, and you're at one with the omniverse. Okay, some pretty mind-boggling stuff.
This is a planetary emergency evacuation. Please remain calm and board your space shuttles.
Even though humanity might not have to leave the Earth in your lifetime, we should start preparing early on. Not only could it take centuries to set up the relocation program, it would take generations to move to a potential new home. That right there is Proxima Centauri b, or just Proxima b. It's the closest potentially habitable planet out there. Its temperatures are in the bearable range, and it could have just the right breathable atmosphere. We only have to get there. How long would our journey last? How many people would we send to populate the new world successfully? And what if it turned out that Proxima b wasn't as habitable as we thought? This is What If, and here's what would happen if we relocated humanity to Proxima b. When astronomers started finding planets outside our solar system, or exoplanets, we realized that there are many worlds out there. That meant that Earth doesn't have to be our home forever, and that we don't have to die with our planet when the sun engulfs it some 5 billion years from now. Now that we've found over 4,100 exoplanets, we've learned something rather disappointing. Not all exoplanets are good for humans to live on. Most of the worlds we've encountered are either ice giants like Neptune or gas giants like Jupiter and Saturn. Only 161 of those planets are terrestrial, like Earth. And when it comes to sustaining human life, being terrestrial isn't quite enough. Proxima b is very promising. It orbits a red dwarf star called Proxima Centauri in a system with 3 stars in it. Proxima Centauri is small. It only has between 7.5% and 50% of our sun's mass. That's a good thing, because the red dwarf Proxima Centauri is so much smaller than our yellow dwarf sun. It burns at a lower temperature. It takes stars like Proxima Centauri much longer to burn through all of their hydrogen supply. Because of that, Proxima Centauri has a lifetime of trillions of years, while our sun has a 10 billion year expiration term. That alone makes Proxima b a good candidate for relocation. That, and the fact that its orbit lies in Proxima Centauri's habitable zone, that means there's the potential for liquid water and comfortable surface temperatures. If we're lucky, Proxima b would have an atmosphere that we could breathe. If it does, the surface temperatures would be in the range of 30 degrees. I don't know about you, but I'd move there right now. I just need to warn you that there are a few problems. A trip to Proxima b would be long and very dangerous. Proxima b might be the closest habitable exoplanet we've got, but that doesn't mean it's close. The red dwarf star Proxima Centauri is about 4.3 light years away. That means that if you could travel at the speed of light, it would take you 4.3 years to get there. Nothing we've built so far can reach that kind of speed. Realistically, a trip to Proxima Centauri in a space shuttle would take 165,000 years, give or take. That's right. Some of the colonists would be born in transit. Some of them would never see the Earth. Some of them would never see Proxima b. They'd just live their lives aboard the spaceship and die in space. How many humans would we need to send on a mission exactly? Well, according to some calculations, 98 people would be just enough. Their descendants would arrive at Proxima b with enough genetic diversity to populate the entire planet. And that's accounting for possible cases of infertility, inbreeding, and sudden deaths. In those calculations, the crew would be traveling on something faster than a space shuttle. Their mission to Proxima b would only take 6,300 years. But don't be surprised. Technology is constantly improving. Right now, a scientific and technological program called Breakthrough Initiatives is looking at how we can get in the neighborhood of Proxima Centauri within 1 generation. Their Project Starshot is working on an ultralight unmanned probe that would reach the star system in just 20 years. Now I definitely need to sign up. But again, Proxima b is really far away. It's so far that we can't even see if it has an atmosphere. It might just happen that we would arrive at a frozen planet with surface temperatures of minus 40 degrees. And even if it has an atmosphere, it might not be the right one. We might still enjoy warm temperatures, but we'd be doing that in spacesuits with oxygen tanks. Or Proxima b could be tidally locked to Proxima Centauri, meaning that one of the planet's sides would always face its star, and the other side would be plunged into darkness. Spaceflight itself could bring some unpleasant surprises. Spending an entire lifetime in a zero-gravity environment would lead the crew members to lose muscle and bone density. They'd be constantly exposed to space radiation. Their microbiomes, immune systems, and physiology would all be different from ours. They wouldn't be the same kind of humans as we are. They would change their values and culture. They might forget all the farming techniques we teach them to sustain themselves in space and on their new planet. They might change their mind about the mission altogether and just turn their spaceship in a different direction. Who knows? They might even come back to Earth and take revenge for all those years they were forced to spend in space. If that happens, I'll be asking for a refund. Sending anyone on a mission like this is a huge risk. We'd need to design and build a vehicle, choose the space travelers very carefully, supply them with all the food and water, and make sure they could become self-sustaining. We'd have to design new propulsion, navigation, hibernation, and life support systems. And we have no way of knowing if Proxima b is actually habitable. Well, now I don't really feel like going there, do you? The year is 2126, and you're watching the Earth rise on a new day from the comfort of your home on the moon. NASA just wrapped phase 1 of building the first city on the moon, and while everyone talks expansion and new architecture, it's still the most lethal environment humans have ever faced. You thought Antarctica was tough. Well, at least it had oxygen. Today, you're going to deep dive into our potential future and experience the reality of living on the moon. And spoiler alert, it's treacherous. This morning, you're taking the monorail out to your gig at the solar farms. Yeah, on the moon, everything has to have power, and solar panels are big, flat things that pack up and ship nicely. This is your first real outside gig, rewiring solar panels powering Luna Prime, and inspecting the ancient radioactive heater units. And you're stoked. This is an exciting time to be a loony. But that title isn't unearned. You've got to be a little crazy to live here. It's extra deadly without any shelter overhead. Micrometeorites fly faster than sniper bullets, and a single tiny asteroid going 50 miles a second can puncture your oxygen tank, crack your helmet open, or put a hole right through the middle of your skull. Every job up here is dangerous work, and humanity's needed to overcome a staggering number of threats just to stay alive. To start, at the moon's equator, there are 14 days of darkness a month. Ugh, scary. And cold. Yeah, let me tell you about the temperature differences. It can reach 127 degrees Celsius in the sunshine, but in the shadows, it plunges to minus 173 degrees Celsius. You ever try starting a car at minus 30? Yeah, this is way, way worse. Plus, there's barely any atmosphere or magnetosphere, which means no protection from the sun's radiation. An abrupt solar flare can shred your DNA to ribbons. There's no air, nothing to eat, and few resupplies. But it's 2126, and humanity's figured out technical answers to most of these problems. But why? Why would anyone go through hell to build a city on the moon? Because everyone who lives up here, you included, is crazy enough to see this moon base for what it really is. A gateway to the universe. Every day feels like history, staging a flight to Mars, the belt, or beyond, or inward. Literally, everywhere in the solar system is hundreds of times easier if we start the journey with a full tank from the moon. And why is that the case? Well, those small steps of Neil Armstrong and Buzz Aldrin are the answer. Low gravity. To launch a rocket from Earth today, you need to achieve 35,000 kilometers per hour, 22,000 miles per hour, and that's just to get into low Earth orbit. To achieve that speed, 90% of the rocket's weight is fuel. Imagine if you had to fill 9 extra cars worth of fuel for your car just to leave your driveway. But on the moon, you're walking around in 16% Earth's gravity. Any launches you make from the moon are therefore 84% easier. And not only that, but with no atmosphere, new launch technologies can be feasible options. Like a railgun that uses electromagnets to accelerate your payload into orbit. It's been an astonishing feat of engineering just to get to this stage. To survive, the city needs constant power, oxygen, and water. Plus comms and server barns, all encased in buildings that can survive extreme environments and store energy. Luna is not just a city, it's a life support system. And every day, there's always the possibility that the pulse of the city could flatline because one computer glitch sends all the oxygen out the back door. Terrifying. And what about gravity? Well, doesn't living in low gravity hurt the human body over long periods of time? Well, stick around till the end of the video to see the details of how you solve that. So, how does this city actually survive up here? Well, it comes down to one thing: materials, resources. So, all NASA's had to figure out in the last century is how to safely duplicate what we have on Earth. Air, water, food, heat, shelter, and not going crazy. Going crazy might not seem like a huge risk. You're out here for an adventure after all, but cabin fever is real. In 2011, the Mars 500 project simulated what it would be like for a year-long voyage to the Red Planet, with crew members undergoing realistic conditions. No real-time communication with family, limited entertainment options, and limited living quarters. At first, the trip was pleasant, with participants all enjoying each other's company. The return trip, however, basically had all participants keeping to themselves. A social ghost ship, and that was only after 1 year of a 500-day planned mission. You're up here on the moon permanently. Now, as you wander from solar panels to the original heater units, which are 95 years old at this point, you wonder, how the heck did they go from a crater to a self-sustaining city? Well, it all started back in the 30s, the 2030s, when NASA built its first habitats on the moon, if you could call them that. Now, you've lived in Luna Prime for 10 years now, so you've done all the touristy stuff, including the historical tour. The first living quarters looked like 4 thermoses welded together with bottle caps. Now, of course, the idea of living on the moon started way before that. People have been spinning stories about it since we were munching mammoths around the campfire. Those sci-fi tales from H.G. Wells to Heinlein, became reality when Armstrong and Aldrin touched down in 1969. Yeah, they famously walked on the moon, but they also lived on the moon for 21 hours. Sure, it was in a lander with about 8 feet of living space, but the two astronauts did report eating and attempting a brief nap. In 1972, after Apollo 17, humans stopped going to the moon for a little while. But in the 2000s and 2010s, a discovery was made that completely switched the narrative. Water. It was discovered in the lunar soil. This made establishing a permanent base a lot more feasible, because we humans need that water. Plans were drawn up to return to the moon and establish habitats. In 2026, the now legendary Artemis II mission became the first crewed flight around the moon in 50 years, firing up humanity's imagination for a moon landing in 2028. And by the early 2030s, NASA had people living on the moon, at least part-time. To start, they lived like Buzz and Neil, sleeping in their human landing systems, which don't sound like a nice place to attempt a nap. But eventually, those blow-up thermos-style habitats became reality, creating a semi-permanent crew presence. The habitats were good at deflecting solar radiation, but the process of getting in and out of them is laborious. Suiting up and leaving the habitat takes hours because lunar regolith gets everywhere, in every gasket, every hinge, on every surface, and eventually an air leak leads to decompression. Not good. So maintenance is an essential part of moon life, unless you want to be the first grave on the moon. Within a couple of decades, once the 3D printers and water mining got going, humanity started building more permanent structures right out of the lunar regolith. Domes. All the domes. Technology already on Earth today allows lasers to weld the lunar regolith together to create a form of moon concrete. It uses a process similar to powder bed fusion, where it melts the regolith powder into a molten state, which then recrystallizes into structural ceramic. Moon laser habitats, yeah! By the time you arrived, Luna Prime was housing over 1 million people, with better transit than most Earth cities. Now, if you're wondering, how did they do it all at scale? How did they secure air, water, food, heat, and shelter for 1 million plus people and not get everyone killed? Well, it's a great question, and the only good answer is science. Well, technology and human ingenuity in the face of overwhelming odds. And science. It was fitting that NASA chose to build Luna Prime on the Shackleton de Gerlache Ridge near Shackleton Crater, named after the intrepid explorer. The ridge is located by the moon's south pole. By wisely choosing to build there, they subverted at least 3 of the most challenging problems the moon presents. First, they avoided the lethal 14-day nights that plague the moon's equator. So new loonies didn't have to spend half their lives in deadly cold darkness. At the South Pole, there's always some sunlight available. It's eerie. The sun hangs low in the horizon all the time, casting long shadows everywhere. But it's a worthwhile trade-off. To keep gear warm in those shadows, NASA brought the radioactive heater units you're checking today. Basically, pellets of plutonium in a protective container that kept machines from freezing solid. They're safe-ish, but a breached unit could give you radiation poisoning. It's still freaking plutonium. If you got sick on the moon, well, there's just the triage center back at the base, but they're not equipped for anything and everything like on Earth. No, up here, you break an arm or get radiation poisoning, you get the same treatment. Rest and hope for the best. Maybe a little Tylenol. Second, sunlight equals power. Solar power. Not only did NASA's nascent city avoid freezing blackouts, its solar farms, like the ones you work on, had access to solar energy 24/7, feeding into massive battery banks, which, as an aside, are basically a third graphite. Nuclear reactors provided constant backup. Third, there are sites of permanent darkness near the poles that never see the light of the sun deep in all those craters. Shackleton Crater is twice the depth of the Grand Canyon. I know what you're thinking. Darkness? Great. But billions of years of permanent darkness created a unique environment that preserved volatiles. That is, ice, which equals water. Delicious, icy water. As an added bonus, there are spots on the South Pole where direct, constant communication with Earth is possible. No interruptions. By just choosing the right location, NASA gave Luna Prime a way better chance of success than perhaps anything else that it did. Soon, NASA started running regularly crewed missions to establish a semi-permanent base. They focused on getting gear to the moon's surface with their crews or through commercial lunar payload services. Basically, space couriers, which delivered rovers and moonfall drones. They also had to deliver basically every meal for every crew member, and they needed to do it for a long time. If you want to grow food on the moon, you need a lot of space, water, technology, and time. On Earth, you typically want somewhere in the range of 1/2 to 1 acre per person for a fully sustainable life. But that much land just isn't feasible to take care of on the moon. Walking around on the surface is cumbersome, and any trip or scratch of your suit is lights out. Hydroponics are one solution for growing food on the moon, vertically. In a temperature-controlled building with artificial light, low-gravity compatible plants can be grown. So, what crops could even grow in low gravity? Well, leafy greens, peas, and vegetables have all been grown in various experiments back in the days of the International Space Station. And back in 2022, Chinese researchers aboard the Tiangong space station grew rice grains for their complete life cycles, from seed to grain and all the way back to seed again. That's an important step because getting anything, even seeds, to the moon is extremely costly. In 2026, Astrobotic quoted $1.2 million per kilogram to get something to the moon. And you don't want to be shipping carrot seeds for the next 20 years. If you can propagate and replant your harvest, well, now you're in business. Moon business. After a few decades of living in thermoses and with enough tools to start building, your grandparents really tackled mass shelter. And that's where all those domes built from moon dirt, regolith, came from. Lunar regolith is a pain. Sharp, sticks to everything, but it's a surprisingly useful building block full of oxygen, silicon, iron, and aluminum. That provides glass and metal for the domes. Why is it always domes on the moon? Well, on the moon, everything needs to be pressurized, and domes are the most stable architecture for pressurized environments. So, humans started making bricks and 3D printing domes out of regolith concrete, mined iron, aluminum, and silicon. Habitats were heavily shielded to protect loonies from micrometeorites and the deadly irradiating solar wind. After a few more decades, humanity had domes, plus oxygen, power, food, and once mining operations in the craters took off, water. So, with all that widely available, NASA started bringing people up to live on a more permanent basis. Lunar space elevators made getting people back and forth more feasible. Some people rotated through a year at a time, but some stayed. Eventually, the habitat became a village, then a town, and then a city. And to be clear, it wasn't the only one. Down the road, China built its own city on the Sverdrup-Henson crater. India and Russia also built nearby. The Artemis project involved the Canadian, Japanese, and European space agencies from the early days, so Luna Prime always had a significant international presence. Fortunately, the Moon, like Antarctica and the International Space Station before it, is generally cooperative. Mostly by necessity. Everybody knows they're in a precarious situation together. Plus, real armed combat is phenomenally deadly in pressurized habitats. If there was ever an incident or a shootout, well, let's just say the general rule is guns in space equal habitat decompression. Oxygen tank explosions, fires, and everybody dies. And as the population of scientists and techs grew, well, they soon started to need other specialists, doctors, nurses, teachers. Yeah, that's right, kids started appearing, as they do when people congregate. In your day, it's no big deal when kids are born on the moon, but that said, humans didn't evolve to live in low gravity, so health problems are abundant. The only solution is to add gravity back. Luna Prime has exercise gyms in spinning centrifuge-like habitats that simulate Earth's gravity. Residences are similarly built to keep people from suffering the worst effects of low G. The diameter needed to sustain comfortable living conditions in Earth-like gravity isn't even that large. According to a NASA study completed in 2015, only about 1.5 kilometers spinning at 1 revolution per minute. Any smaller than that, and your head experiences significantly less gravity than your feet do, so bending over and turning around become nauseating experiences. Though with enough spin-up time, people could survive in habitats that are as small as 50 meters, spinning at 6 revolutions per minute. You don't, but it is theoretically possible. Living in tight, regulated quarters with the potential for death on the other side of every wall isn't for everyone. But you love it. You used to be terrified of the micrometeorites that you can see have hit the lunar surface, but you've never actually seen one. It feels like a distant fear now, though it's not really something that'll happen to you. And you love being on the surface of the moon. It's like being a couple hours drive outside the city and looking up at the crystal clear night sky. It's just you and the stars, looking up into the totality of the universe. Because the moon has no atmosphere, night and day have no difference when you look up in the sky. It's always black, always starry, and since the moon is tidally locked with Earth, you always get to see your homeworld whenever you want. Just look up. As you check the old heaters and scuffle over the footsteps of those techs and astronauts who established Luna Prime, well, you can't help but appreciate their work. And imagine what it was like way back in 2026, after Artemis II. The world is at a tipping point, finally planning to go back to the moon for the first time in 50 years. Within a decade, NASA and its fellow space agencies would build a base on the moon that would signal the potential exploration of the solar system, of the universe, to the whole of planet Earth. You imagine what it would be like to look up at the night sky for the first time in the mid-2030s and see another world with the lights on.
What if we could engineer a gigantic megastructure capable of harvesting every bit of the sun's energy? Something known as a Dyson sphere. How long would it take to construct this mega shell? Where would we find all the materials needed? And what could we do with the structure once we finally built it? This is What If, and here's what would happen if we could build a Dyson sphere around the sun. The idea of a Dyson sphere was, well, stolen from aliens. In 1960, astrophysicist Freeman Dyson theorized another civilization that found a way to meet their ever-increasing energy and space demands. They rearranged their solar system. This hypothetical advanced civilization built a hollow sphere around their own sun
and provided themselves with an incredible amount of energy and habitable real estate. But what about us? How would we go about building this space-level structure? Theoretically, if we built a Dyson sphere, we'd have access to a colossal 400 septillion watts of solar energy. That's 1 trillion times more power than our entire civilization consumes today. The problem is, no known material is strong enough to handle all the space radiation. And even if we created one in very large quantities, a tiny gravitational pull towards the sun would make our solid sphere uninhabitable. Not to mention that it would be totally unstable. Every meteor strike would push a part of the sphere towards the star. But all these issues can be solved with a simple adjustment. Instead of building a solid Dyson sphere, we could build a Dyson swarm, a myriad of solar collectors with their individual orbits around the sun. Let's start with a small station, one that's able to provide the energy needed for this whole construction project. We'd begin on Mercury. It would become our space mine for the iron and oxygen we'd need. From those elements, we'd make highly reflective solar collectors. The giant mirrors would reflect light into a small solar power plant. From there, it would beam the energy to where we need it. We'd probably demolish Mercury entirely before we moved on to Venus, Mars, and the outer planets. Even nearby asteroids would be decimated. However, even just deconstructing Mercury would supply us with enough energy to power up our supercomputers and boost interstellar exploration. Maybe we'd even build Earth-like oases, large rotating space colonies in the habitable zone of our solar system.
If humanity was forced to leave Earth and settle on another planet, where would we go? Well, Mars seems promising and it's close to Earth, but if you actually needed to survive there, well, good luck. Mars will freeze you, suffocate you, nuke your DNA with cosmic radiation, and crush your settler dreams under a dusty red sky. It's not a second Earth. It's a slow-motion death trap. Surely there's got to be another place out there for us to survive. Well, today we'll look at 6 of the most promising exoplanets to see which one could become Earth 2.0. We'll start with the closest planet to Earth, Proxima Centauri b. This exoplanet is only 4.24 light-years away, and its orbit is in its star's habitable zone. In the case of a huge disaster event like our sun exploding and wiping out the entire solar system, this planet would make for a great quick getaway, right? Well, not so fast. 4 light-years is still an incredible distance. If you owned a spaceship that could travel at the speed of light, it'd still take you over 4 years to get to Proxima b. And face it, you don't have that kind of technology, do you? The fastest object humanity has ever built is NASA's Parker Solar Probe, and it travels at about 700,000 kilometers per hour. That's 430,000 miles per hour. You can't travel in this probe because it's not meant for transporting humans, but if you could, it would take you 6,500 years to reach your destination. Yeah, not ideal. Space is really, really vast, and hopping from one planet to another takes a long time. So let's just say that huge advancements in the fields of cryogenics and engineering were finally able to deliver you and your crew to Proxima Centauri b. Okay, now you're about to start a whole new civilization. The first thing you'd notice after you touch down is how dim and red your new sun is. The star you're looking at, well, it's called Proxima Centauri. It's a red dwarf star that's 7 times smaller and hundreds of times dimmer than the sun. Proxima Centauri b is tidally locked to its star, Proxima Centauri, which means that one side is always facing Proxima Centauri and the other side is in constant darkness. Dayside temperatures here are hot, anywhere from 40 degrees Celsius to 100 degrees Celsius. That's up to 212 Fahrenheit. And the night side? Well, this side is too cold, with lows close to minus 150 degrees Celsius. But smart you did your research and you landed in the planet's terminator zone,
That's the area between constant day and never-ending night. And it's balmy. Your thermometer reads at 15 degrees Celsius. That's 60 Fahrenheit. Great start. Now, as you begin to explore the planet, the ground is crunching beneath your feet. The wind is blowing dust in the air. But you're not worried. You've got a pressurized suit to keep you alive. Unfortunately, the atmosphere here is unbreathable. There's way too much carbon dioxide and almost no oxygen. Take your helmet off and it's game over. Now, you have to plan for a shelter. You see, the thing about red dwarf stars, like the one you're facing, Proxima Centauri, is that they're violent and can send massive bursts of X-rays and ultraviolet radiation your way at any time. Setting up a solar storm shelter will be your first order of business. After 1 week, your crew has set up a basic habitat and shoveled a ton of soil. You've covered up the habitat with some of this soil to provide extra insulation. This is where you'll sleep, eat, and survive for the next few weeks. For power, you've set up wind turbines, making good use of Proxima B's breeze. If you hear a flare alarm, run to the radiation bunker you dug out in the ground. Here, you'll be safe until the star calms down. Alright, by the end of the first month, you'll have built a second hub and you'll have a little greenhouse going. You'll be able to grow potatoes, algae, maybe even kale. It's not exactly gourmet, but it's enough to sustain you at first. Now, the first couple of months here would be a lot of engineering and strict rationing, but soon you'd be able to venture a little further and really start exploring the planet. And you'd get to be the one to name the first features. Twilight Spires, Echo Crater, Flatline Ridge. That last one is for Chase, he who dies in space. By the end of year one, you'd finally be settled on this planet. You'd have everything you need to live here comfortably, more or less. You'd have a living quarters, a lab, power grid, a radiation shelter, and the greenhouse. Your menu would expand beyond kale and potatoes to maybe something a little more tasty. Your outpost may be ugly, dusty, and constantly threatened by intense solar flares, but it works. You've made it. You live in a ribbon of twilight between fire and ice. One step too far in either direction, and you die. But you stay. You still couldn't take your helmet off or your spacesuit. The air here is still, as I said, unbreathable, but you're here for the long term. Hashtag Planet Goals. Okay, now, after 10,000 years, your settlement has really made it. It's grown and evolved, and there are people everywhere. The people living here have spent centuries making use of oxygen generators that converted carbon dioxide into oxygen and have made the atmosphere breathable, at least for short periods of time. They still have to worry about humongous solar flares, but with bunkers all around the habitat, they've got it under control. Unfortunately, your generation of settlers has also been severely irradiated by the star. As much as you tried to avoid it, the radiation still affects the population. That's why you mostly stay in the habitat rather than go out and explore the planet further. Eventually, humans would outgrow the habitat and outgrow the Terminator Zone. They'd have to adjust to living in extreme cold or unbearable heat. And it's not the kind of life they pictured when they signed up to come here. Now, while Proxima B is largely a success, let's explore other worlds too, like TRAPPIST-1e. This exoplanet is 40 light years away from our galactic residence, and it's only slightly smaller than Earth. TRAPPIST-1e orbits an ultra-cool red dwarf star called TRAPPIST-1, and it has 6 other Earth-sized neighbors, though only 3 are in the star's habitable zone. Luckily, TRAPPIST-1e is in the Goldilocks zone. That means it could have liquid water on its surface. And now, you're about to step onto this alien surface and make it your new home. Okay, you've finally touched down on TRAPPIST-1e, the most Earth-like of all the planets in the neighborhood. This alien rock will give you hope. As you step onto its soil, you'll see all 6 other TRAPPIST planets the way you see the moon from Earth. You'll also notice the dim sun hanging low in the sky. Not the dim sum, the dim sun. That's TRAPPIST-1. This star is barely 9% the mass of our sun, and it glows hundreds of times fainter. On TRAPPIST-1e, you'll live in an eternal sunset. As you walk, the slightly weaker gravity would make your movements feel oddly graceful. Gravity here is about 90% of Earth's gravity. Now, just like on Proxima Centauri b, the best place to land here is the Terminator Zone. That's right, TRAPPIST-1e is also tidally locked to its star, and you don't want to boil on its hot day side or freeze on its frigid night side. The temperature in the Terminator Zone might be brisk, but not unbearable. Just a few degrees above 0 degrees Celsius, 32 Fahrenheit. You take a deep breath inside your pressurized suit and you get ready to do some work. Your first priority is to establish life support and safety. The atmosphere on TRAPPIST-1e could be breathable, but you still keep your helmet on. You'd need to test the air for toxins and harmful microbes first. Now, TRAPPIST-1e has one thing Proxima Centauri b does not: water. With an oxygen-rich atmosphere, water, gorgeous views, and a never-ending sunset, this planet is a pretty good contender for Earth 2.0. Your team has now confirmed the air is breathable, but you don't want to risk it. Not yet. You didn't travel all this way from Earth just to die on this rock. You'll set up your main habitat near a water source. Your crew will deploy a water extraction system to filter the water. You'll also set up a greenhouse module and start growing plants for food. But the dim light from the star isn't enough to give your plants the energy they need, so you'll rig up some LED lights above your greens. Kale is still on the menu. Just like on Proxima Centauri b, you're going to need a radiation shelter. Yeah, this star, it spews out violent bursts of radiation, and you never know when to expect them. After your first month on this planet, you'll be pretty confident that you could make it work here. I mean, what choice do you have? It's not like you could turn back and travel the 40 light years back to Earth. Your camp is growing. You now have a larger radiation-shielded habitat and a nuclear power source. And here's a relief. The atmosphere is safe. So is the environment. If the air or soil had toxic chemistry, you would have seen the effects by now. Instead, you've discovered that TRAPPIST-1e has near Earth-like conditions. I mean, apart from the unpredictable and violent solar flares. Luckily, most of those are happening on the day side, so as long as you don't venture too far from the Terminator Zone, you'll be fine. You'll be doing a lot of science, further testing the air, soil, and water for chemical composition and potentially even some microbial alien life. Yeah, you might not be the first settler on this world. You'd even start taking off your helmet. It's still risky, but TRAPPIST-1e seems safe for now. A century has gone by, and now the human population has grown to several hundred people. Your settlement is now self-sufficient. Over the decades, more ships arrived from Earth. The new arrivals brought fresh supplies, more settlers, and updated equipment. With these advancements, TRAPPIST-1e now has multiple settlements spread across the planet. Once again, you succeeded on an alien world. But there's still that issue of solar flares and radiation. While TRAPPIST-1e might not be so bad for life, it's still not perfect. And there are so many other alien worlds out there. Don't settle on this one just yet. This world ahead? That's K2-18b. K2-18b is one of the most exciting exoplanets ever discovered. It lies just 120 light years away and orbits within the habitable zone of a red dwarf star. This world is about 2.5 times the size of Earth and has about 8.5 times as much mass. The hope is it's a super Earth covered in oceans. The worst case scenario, it's a mini Neptune. It likely has a thick, hydrogen-rich atmosphere. Good for trapping heat, terrible for breathing. But here's the exciting part. Scientists have detected methane, carbon dioxide, and even dimethyl sulfide, a chemical that's produced by marine life here on Earth. That could be a major clue that we're not alone. If you were to settle on K2-18b, you wouldn't land on solid ground because, well, there might not be any. And if there is, the volcanoes and quakes might make it too unstable anyway. So what do? Well, you build a floating habitat. And no, I'm not talking about a habitat on the water. I'm talking about one hovering just above the cloud tops. An alien cloud city. You'd need shielding from intense radiation, sturdy structures to resist weather, and a way to extract water and nutrients from the atmosphere or the ocean. It'd be dangerous and you might fail, but at least you'd try something new and exciting. All right, let's look at another potentially habitable world, Kepler-186f. This rock made history. Kepler-186f was the first Earth-sized exoplanet ever discovered orbiting in the habitable zone of its star. When astronomers announced it in 2014, it became a possible Earth 2.0. That's where the good news starts, and also where it kind of ends. Kepler-186f orbits a small, cool red dwarf star called Kepler-186. The planet sits right at the outer edge of the habitable zone, which means it's not getting a lot of sunlight. To be exact, it receives only about 32% of the solar energy that Earth gets from the sun. Without a thick, heat-trapping atmosphere, it's likely a frozen world. Now, if there is water ice here, you'd need a serious thermal energy system to thaw it. And forget about using solar panels, at least not as your main power source. That red dwarf sun is just too faint. You'd have to rely on nuclear generators, like NASA's kilopower fission reactors, to power your base and keep it warm. There's also a logistics problem. Kepler-186f is the only planet in its system's habitable zone. The other known planets orbit much closer to the star and are scorched. So if this place doesn't work out, there's no plan B nearby, and you're 500 light years from Earth. No resupply missions, no rescue ship, no turning back. And if you think 500 light years is already pushing it, well, you might not like where we're going to take you next, because this next planet is 1,200 light years away. Kepler-62f is a super-Earth exoplanet in the habitable zone of its star. The star is called Kepler-62, a K-type orange dwarf that's cooler and dimmer than our sun. The planet itself is about 1.4 times the size of Earth, and it orbits much further out than Earth does. That means it receives significantly less warmth and light from Kepler-62. This would make most of Kepler-62f very, very cold, especially if it lacks a thick atmosphere. Large portions of the planet could be permanently frozen. But if you give this world the right atmosphere, everything changes. If Kepler-62f had an atmosphere at least 3 to 5 times thicker than Earth's, that was mostly made out of carbon dioxide, well, then it could trap enough heat to make parts of the planet temperate and stable. If you were setting up a settlement here, your best bet would be to pick the warmest spot on the day side, ideally near the equator. You'd still need radiation shielding, atmospheric processors, and heated shelters, but you could make it work. Kepler-62f is 1,200 light years from Earth, so you're definitely not commuting back and forth. But if you're willing to terraform a little or a lot, this frozen super Earth might just have what it takes to be your future home. Okay, let's take a little break from the Kepler family and swing by a different neighborhood. TOI 700 is a cool, quiet red dwarf star just 100 light years away. And guess what? It's not constantly erupting with flares trying to cook you alive. This is progress. This star hosts 4 planets, and the real standout is TOI 700d, because it's the only one in the habitable zone. TOI 700d is about 20% larger than Earth, with gravity just a tad stronger than what you're used to. And it gets about 86% of the sunlight we get back at home, which sounds pretty perfect. Where I live, I feel like I only get about 50% of Earth's sunlight. The only hiccup with TOI 700d is that this planet is, say it with me, tidally locked to its star, which means one side is always day and the other side is always night. But you already know what to do. Yes, that's right. Head for the Terminator Zone. Of course, you'll still need pressurized shelters, radiation shielding, and life support systems while you find out if the atmosphere is breathable. And while TOI 700d seems calm on the surface, this planet comes with a few surprises. For one, we don't know what the air is made of. It could be oxygen-rich and friendly, or it could be a carbon dioxide soup that melts your lungs. So don't ditch the helmet just yet. And what if there is an atmosphere? Well, buckle up. That much heat on one side and cold on the other can create wild weather systems. Think supersonic winds howling through your camp at all hours. And then there's the water, or the lack of it. We haven't confirmed any surface water yet, so you'll either have to bring your own or extract trace amounts from the air, if the air exists. Not sure I like TOI 700d so much. So all these alien worlds have potential, and there are plenty more out there for you to explore and possibly settle on. As long as you know that you'll be building an entire civilization in a place where everything wants you dead. Yeah, it'd be a lot of effort not to die on these worlds. But persevere, because perishing on them wouldn't be pretty. The sun has begun its red giant phase, expanding like an overheated plasma-filled balloon. It's about to consume Mercury and then epically engulf Venus and eventually swallow Earth. Even now, it's broiling our planet to bone-scorching temperatures. This is Earth 5 billion years from now. But how did we get here? Well, let's take a journey through time, from this very moment you're watching this video, all the way to that day 5 billion years in the future, when the sun is far bigger, brighter, and way too close for comfort. It's about to get hot, radioactive, super volcanic, and deadly. The next 100 years of your life is going to be one of the most unpredictable centuries in human history. The impact of tech, AI, climate change, medicine, and renewables are going to be nearly immeasurable. But if you're thinking about what things are going to be like in billions of years, well, you gotta think bigger than just your own backyard. Mostly because every backyard on Earth is eventually going to be incinerated. We have to think galactic. In just the next decade, humans will send probes to far-flung planets and moons like Venus and Europa. We'll send people to explore the South Pole of our own moon, and it'll be the first time this century that anyone's set foot on our closest cosmic neighbor. Within 50 years, you might be watching the world go by from a lunar moon base, or even exploring the surface of Mars. Within a couple of hundred years, you, thousands of settlers and whatever robotic pets you want to bring along with you will be living on Mars permanently. Back on Earth, humans will be working to get the planet's average temperature back down to a manageable number, while you will set out to terraform the red planet. Your goal is to bring a greenhouse effect to Mars to warm the place up. In the darkest corner of our solar system, things would be getting a little heated. Pluto would cross Neptune's orbit and become closer to the Sun than the ice giant. But don't worry, this happens every couple hundred years and only for some 20 years at a time. And speaking of the outskirts of the solar system, humanity will finally discover local extraterrestrial life, if it exists. The moons of Enceladus, Europa, Titan, and Triton all have potential for life in their ice-capped oceans. This life could be microbial or feature wildly advanced multicellular body designs. The next time Pluto swaps orbital spots with Neptune, just shy of the year 2475, humanity and our robotic overlords will finally finish terraforming Mars. Or underlords. We'll see. But that's right. Finally, planetary scientists, chemists, engineers, biologists, basically every kind of scientist that's ever existed, used barely comprehensible technology to solve the unsolvable problems of living on Mars. Like overcoming the lack of heat, atmosphere, oxygen, water, a magnetosphere. Together, we created a red planet where human, transhuman, and cyborg relatives can walk freely on a remarkably Earth-like surface. Your backyard could include a view of a pale blue dot, whether your backyard is on Earth or on Mars. After that, we'll start settling every other available rock in the solar system, including asteroids and the massive moons of the gas giants. You'll move to Venus to build cloud cities and commute in helium-based zeppelins. Now would be the time to start terraforming Venus. First we move there, then we terraform. Now, these projects take a long time, but fortunately, the human lifespan has increased radically. Medicine of the 26th century makes the most advanced treatments of today look like leeches and bone saws. By the year 2500, you will live longer than ever, comfortably reaching 150 years of age on average. And in your old age, you'll be golfing on Mars and clogging up tech hotlines. On a larger scale, humanity has reached a long-standing theoretical milestone. We've finally become a Kardashev Type 1 civilization. The Kardashev scale was created by famed astrophysicist Nikolai Kardashev as a way to envision a civilization's technological prowess based on its energy consumption. A Kardashev Type 1 civilization is capable of harnessing and using all the energy roughly equivalent to what our Earth can potentially provide. That means you, if you're living on Earth, have figured out how to use every bit of wind, tide, solar, biological, geothermal, chemical, fossil, and nuclear energy on the planet. Wherever you and your brainy pals see a source of energy on Earth, well, you've already figured out a way to use it. And if you need more energy, you're gonna need to go further afield. Within a couple of hundred more years, say by the year 2700 or 2900s, you've actually terraformed Venus. It feels weird to me to say the 2900s, like just the other day I was saying the 1900s. Is it just me? Yeah, it's just me. To turn a planet like Venus into something resembling Earth, you'll have to perform solar system level engineering. Take the most impressive builds humanity's ever pulled off, from pyramids to hadron colliders, space stations, and magnify them exponentially. To make a hell planet like Venus habitable, we're talking about pushing the planet into a different orbit, creating magnetospheres, changing the atmosphere, steering comets into the planet to create water sources. Yeah, I didn't say it would be easy. Okay, once you've managed to terraform the inner planets, well, you'll move on to the outer planets of the solar system, or start building colossal megastructures that encircle the sun. Yeah, humanity will build a Dyson sphere, a habitable mega spacecraft that harnesses most of the power of the entire solar system, which means that sometime between the year 3000 and 5000, humanity will upgrade to a Kardashev level 2. You're now part of a civilization capable of capturing the power of the sun. At this point, humanity has spread further afield than just the solar system. Now, you'll move into interstellar space to explore deep within our Milky Way galaxy. Now, I say humanity, but let's be realistic. Pushing our bodies to survive in space means we'll need to be able to bioengineer our frail, earthbound bodies to withstand space radiation. With the help of nanotechnology and AI, your body, just like civilization, will get a serious upgrade. Homo sapiens, which haven't evolved much genetically, will be changing their bodies at will, interfacing with technology, and maybe even becoming more machine than human. All this travel in low-gravity environments will make you taller, and your eyes will evolve to be bigger. My eyes bigger? Or you might not exist anymore. Yeah, that's the thing about civilizations. They tend to doom themselves the further they advance. Maybe it's the unchecked tech, or power struggles, or AI, or climate collapse, or American politics. Whatever it is, the idea is that the smarter a species gets, the more dangerous the tools it builds. And eventually, it builds one that it can't control. The idea is called the Great Filter, and it might explain why we haven't seen any advanced aliens out there. Some scientists argue that in 10,000 years, there's a 95% chance humanity will be no more. If I had to guess, well, if we accidentally terminate ourselves with homicidal AI robots. But if you didn't survive past that mark, well, you wouldn't see the way the Earth dies. So let's keep you alive a little longer. Okay, at this point, Earth will start to resemble pre-terraformed Mars. And no, it wouldn't be a hot world. Rather, it would be a frozen one, because in 100,000 years, if global warming hasn't torched the planet entirely, Earth will plummet into a new ice age. Yeah, instead of rising heat, you'll be looking at rising glaciers. If we haven't built a proper Dyson sphere that can act as a planetary furnace, things are gonna get very chilly. And then, boom! The violent eruption of the Yellowstone volcano. Ash and pumice will jettison into the atmosphere, block the sunlight, and make Earth even cooler than Ice Age cold. If humanity hasn't been wiped out by now, we will successfully transition into a multi-planetary space-going species, entering a new era of Homo sapiens. Okay, you worked really hard, and finally, human civilization became a Type 3 on the Kardashev scale. Now, we harness and use all the energy created in an entire galaxy. Billions of stars, black holes, and interstellar winds now feed our unimaginable power grid. Dyson spheres encase stars like glowing pearls. It's a new era, and not just for you, but for the entire Milky Way. And even though you've harnessed the power of the entire galaxy, you still might not survive the dangers of the universe. Now, on a cosmic level, we're way too close to interstellar time bombs, like the White Dwarf in the T-Pyxidus system. T-Pyxidus is located over 3,000 light-years from Earth. It's an odd binary star system that keeps going supernova. The White Dwarf in the system seems to be building mass, putting on the beef, and if it continues to do so, watch out, because even though it's thousands of light years away, it's still close enough to cause our planet damage. Supernovas, or even hypernovas, are violent and majestic events. They're the end of stars' lives, but they're responsible for producing most of the heavy elements in the universe, like iron, the iron in your blood. But in roughly 10 million years, this one could explode with a ferocity that ripples across the universe. The gamma radiation alone, stronger than 1,000 solar flares, could decimate Earth's ozone layer. If you're still wandering around at this point, you'll need to solve some kind of supernova defense, or that could be the end of life on Earth as we know it. At this point, humanity wouldn't be anything like what you know it to be. It'll be evolved, in the same way that imagining the lives of our ape-like ancestors 10 million years ago is an almost impenetrable gulf, despite our shared unbroken genetic chain. That's a time before Lucy, the Australopithecus. It's pre-human. And this is well past human. It's post-human. We could just be machines, or machine-human hybrids, or something entirely different. Okay, in 50 million years, Mars will tug one of its moons, Phobos, way too close. When Phobos reaches the Roche limit, that's the point beyond which Phobos' gravity wouldn't be able to hold it together, this moon will crumble and form a faint ring around Mars. On Earth, the continents of Africa and Europe will smash into each other, creating a rift of mountains high enough to rival the Himalayas. And this continental shift and the rise of new mountains will be violent for Earth. But the dangers can also come from the sky. 100 million years from now, an asteroid will hit the Earth. And not just any asteroid, the dinosaur-killing kind. But in this case, the human-killing kind. We better learn how to deflect large asteroids by then, because if we don't, it'll be game over for life on Earth. I wonder if dinosaurs ever had that thought. Earth's tectonic plates keep on drifting. At this point, they'll pull a reverse Pangea and ram into each other, forming a new supercontinent, Pangea Proxima. Every continent, with the potential exception of Antarctica, will eventually collide and create a giant landmass, surrounded by a planet-wide ocean. Supercontinents are places of extremes. Extreme temperatures, extreme flooding, extreme drought, extreme mass extinctions, mega monsoons, and hyper hurricanes. And if we're still around and still keeping an eye on things, this will also be the time when you can watch Saturn go strangely ring-free. Its bright, iconic rings will eventually get pulled into the gas giant. Within 500 million years, you'll witness even bigger supernova threats, like WR104 out in the Sagittarius constellation, 8,000 light-years away. Once it goes supernova, the gamma radiation will pulverize our ozone layer, causing extreme acid rain and set off another extinction-level event. In 1 billion years, well, things will get dark. No, not visually dark. Visually, it'll be quite the opposite. The sun will start emitting more energy than ever, and that will make Earth's temperature go way up. All that excess solar energy will interrupt the carbon cycle, kill photosynthesis, and cause oxygen levels in the atmosphere to drop. No plants, more problems. If anything were still alive on Earth at this point, well, it won't be for long. Most oxygen-breathing life on the planet will have died out. Only anaerobic creatures will survive, for a while. Those are organisms that live and grow in environments without oxygen. As our planet is going through this atmospheric change, you'll have to leave Earth behind, or move it to a different orbit if you still know how to do that old trick. In roughly 2.5 billion years, the changes get intergalactic. Our homey Milky Way galaxy will collide with the Large Magellanic Cloud, a relatively small dwarf galaxy nearby. And what a show that'll be. Two galaxies smashing into each other? The sun will glow up, and not in a good way. Soon, it'll reach its hottest point and grow 10% bigger than it is today. The outer edge of our solar system will see some major changes. One of the biggest moons in the solar system, Neptune's moon Triton, will drop under its Roche limit and get torn apart by the blue ice giant. Not long after that, celestially speaking, our Milky Way will collide with the nearby Andromeda galaxy. Over 1 trillion stars will smash into the Milky Way. The two supermassive black holes at the centers of the galaxies will eventually merge and create a new, even more supermassive black hole. And Earth? Well, at this point, it'll lose all its water. Okay, 5 billion years from now, the sun will begin entering its red giant phase. It'll start expanding toward Mercury, Venus, and Earth. Even if the sun doesn't fully consume Earth, things are gonna get hot. Too hot for us or any other terrestrial life to handle. Of course, there will no longer be any life on Earth. It's possible that Mars, that you terraformed way back in the year 2500, won't be consumed, but it's gonna be far too hot to keep inhabiting. The habitable zone of planets in the solar system will really only include Saturn and Jupiter at this point. And since they're gas giants, well, they aren't super handy for humans. But it's possible you've terraformed their moons and you got a comfy spot on Ganymede or Titan, or your own personal Dyson sphere. Either way, to survive in the universe in 5 billion years, humanity will need to have slipped the surly bonds of Earth and flown across the galaxies. Can we turn these alien worlds into habitable planets? Well, that's a story for another What If. There are trillions of planets in the universe, but even with our most powerful telescopes, we've never found a single trace of life out there. And no alien civilizations ever found us. It could be we're just not advanced enough to be noticed, or we're looking for the wrong things. So it's time to upgrade. Make some interstellar noise, build some megastructures, megascopes, and find out whether we're actually alone in the universe. Today, we're going to speed up Earth's evolution and become an intergalactic Type 3 civilization on the Kardashev scale. That is, if we don't go extinct first. Of course, to become a Type 3 civilization, well, we'll need to reach Type 1 status first, because currently we are... that's right, 0.73. The scientists ran advanced machine learning computations a couple years ago, and the math said that's where we are on the Kardashev scale, which doesn't sound very impressive. Now, if you're wondering, what the heck is a Kardashev, and what's their scale, and what does it have to do with civilization? Well, that's completely fair, so let's back it up. The Kardashev at the heart of the Kardashev scale is Nikolai Kardashev. He was an astrophysicist and scientist, part of a team looking for extraterrestrial signals in the 1960s. In 1964, he wrote a short, elegant paper, Transmission of Information by Extraterrestrial Civilizations. It proposed that